All right, the last section in chapter 2 is called related rates, and these are, well, what they're called. They're rates of change that are related to each other, and they work really well for word problems, which is bad news, I guess. But here we go. Just like everything else in the last two sections, you really know how to do all this stuff already. It's really just implicit differentiation. So we already learned these two. This derivative, since it's with respect to x, is 4x cubed. This derivative, since it's with respect to x, is 4y cubed, but then times the derivative of y with respect to x, which I have been writing as y prime a lot, but I'm going to stop now for purposes of this section. So, for related rates, usually we're talking about the rate of change with respect to time. Like the rate at which you're driving is miles per hour. If you look at these rates, and derivatives are rates, these are rates with respect to x, which is just a variable. So, since these are going to be applied examples, like real life examples, we're not going to use just x and y, which basically stand for anything. We're going to use t, because t stands for time. That's the only new thing. So the derivative of x to the fourth with respect to t is no longer just 4x cubed, because that's what it is with respect to x. You now have to multiply the derivative of x with respect to t. That is it. So basically on these problems that you're going to do, everything's implicit, because all these variables are going to be x's and y's and b's and whatever. None of them are going to be t. So this one is 4y cubed times dy dt. So there's really no difference now, whether it be an x or a y, because the variable that we're differentiating with respect to is now t. So that's it. You have to follow rules. So this one is going to remind you, follow the rules. This is a product rule. First times the derivative of the second plus the second times the derivative of the first. I will simplify this. We have a 4 in common. We have an x cubed in common. We have a y cubed in common, and we're left with x dy dt plus y dy dt. Now, I'm going to say this, no longer use like a y prime for the derivative, because that usually means dy dx. So this t means something, so we want to keep it as dy dt or d whatever dt. So here's an introduction to where we actually have a quote unquote real world problem. If you recognize this equation, it's the volume equation of a sphere. So say for some reason the sphere is changing its volume. Now the common application for this is, say we have a perfectly round spherical balloon and you're blowing it up. That would mean the volume's changing with respect to time, and so is radius. So this is your regular volume equation. We're going to make this a related rates equation. To make a related rates equation, you differentiate both sides with respect to t. So you have two variables, v and r. So the derivative of v with respect to t is exactly what I just said, the derivative of v with respect to t. 4/3 pi is a constant multiple. You can ignore it. The derivative of r cubed with respect to t is 3r squared. Derivative of the outside, leave the inside alone, times the derivative of the inside, which is dr dt. Now you simplify. So dv dt, the rate at which this balloon is changing its volume, is equal to 4 pi r squared times the rate at which its radius is changing. So that's it. Now you could have gone right from here to here if you think about it. Think about the derivative of pi r cubed. You bring down the 3, it cancels. You're just left with r squared, but you do what you need to. And I think this next question, and we'll end the video after this because I don't want it to get too long, but before you leave, this is an important question. When you're doing real world examples, sometimes it's hard to figure out where to plug things in. So I'm just like this. The units will tell you a lot about where you should plug things in. That's why this question right here is very important. For each variable in this derivative, what might be a possible unit? So I'm going to So the measurement of volume is three-dimensional. So let's just say we're measuring the volume of a room. You take feet by feet by feet. You have to make length times width times height. Feet times feet times feet, which would be feet cubed. Now just think about it. Volume is a three-dimensional thing. So the units should be units cubed. If you're talking about area, length times width, like the area of a floor, you'd take feet times feet, which is feet squared. But then again, think about it. Area is 2 dimensions. So that's where this 2 comes in. If you're just measuring the length from here to there, that's a one-dimensional thing, a line. That would be in feet. So dV is the rate at which volume is changing. Volume would be, and I won't use feet here, let's just pick another unit, inches cubed, because it's a volume, over dt. That's a time, let's say seconds. So that dV dt would have a unit of a length cubed over time. R is just a length. You measure like the radius of a circle. That could be inches. And r squared would end up being inches squared. dr dt is the rate at which a radius changes. Again, radius is in inches over time, dt, which could be seconds. Now, if you look at this equation in total, the left side is inches cubed per second. The right side is inches squared, because of this 2, times inches per second, which is inches cubed per second. So it balances itself out. So that's a really quick, short introduction to related rates. I'm going to make one more video as far as how we're going to handle some of these problems.